We've been talking about basic chemistry, and at this point you should feel comfortable defining terms, doing conversions. Many of you were successful in the SIGFA quiz. Some of you need to go back and review the videotape, come in for help, whatever you need. And today what we're going to do in a two-part lesson is to classify matter, elements, compounds versus mixtures. And then in the second half of the lesson, we'll discuss properties and changes associated with matter. And that will end our very large chapter 1, and you'll be tested out next week. What we're going to do today is classify matter. I'm going to show you a brief little videotape that helps to put some of this into perspective. We know that matter is anything that has mass and takes up space. And matter is comprised of very tiny particles known as atoms. Atoms are the building blocks of matter, similar to the way that you learned about, for example, proteins last year, where amino acids were the building blocks of proteins. For those of you who used to play with Legos, if you're constructing a building, for example, your building block would be a Lego, although I think they have some cooler toys out now with the magnets, and we play with those at home. It's fun. This pyramid here shows you how you classify matter. It is different from your food pyramid in the sense that at the top you have materials. And a lot of these terms are defined below, but any specific type of matter is known as a material. And you can break it up into homogeneous versus heterogeneous materials. What does the prefix homo mean? Same. Good. So homo means same, like homosexual, homologous chromosomes. What other word from bio had homo in it last year? Think about genetics. I think I heard it. Homologous I mentioned with the chromosomes. Homozygous, that was the one I was thinking of as well. Very good, same. So homozygous alleles like big A, or little a, little a. In contrast, if you had big A, little a, you're not homozygous, you're heterozygous. So hetero means different, okay? With your homogeneous materials, you can have pure substances, or you can have homogeneous mixtures, and the video will go into that a little bit more. With your heterogeneous materials, you can have heterogeneous mixtures. So what we're going to see from the video is the difference between pure substances and mixtures, and then we'll discuss it below. And again, a lot of those key terms are defined for you. Let's take a look at a short video.
Website today. All the stuff in the universe can be grouped into one of two categories. Stuff is either matter or it is energy. We've already learned that matter and energy are related to each other in the mass-energy equivalence, which was shown by Albert Einstein in his equation E = mc². For now, we're going to forget about energy. We're just going to focus on matter. Remember that matter is anything that has mass and takes up space, or in other words, has volume. This is a very broad definition, so let's break it down so we can better understand the different types of matter. One way that we can categorize matter is based on this purity. Most of the matter in the universe is found in a mixture. And a very small amount of matter in the universe is found as a pure substance. A mixture is a system of matter that is made up of two or more different substances, or types of matter. A great example of a mixture is a pizza. The different substances of the pizza are physically combined together, rather than chemically combined, which is a more permanent combination. In most mixtures, you can pretty easily separate the different substances. A pure substance, on the other hand, is only made up of one substance, in other words, only one type of matter. You can't break it down into any different types of matter. An example of a pure substance is aluminum foil. If you started to tear apart or break down the aluminum foil, it's still going to be aluminum. And so it's a pure substance because it's only made up of one substance or only one type of matter. Let's focus in on mixtures for a moment. There are two categories of mixtures. The first type of mixture is a mixture where you cannot see the different parts of the mixture. We call this type of mixture a homogeneous mixture. The root word homo means same. And so these mixtures appear to be the same throughout the mixture. You can't see the different parts of the mixture. A good example of a homogeneous mixture is a glass of tap water. Tap water has many different substances that are dissolved in it. However, the glass of tap water appears to be perfectly clear. It's a homogeneous mixture. The other type of mixture is the type of mixture where you can actually see the different parts of the mixture. We call these types of mixtures heterogeneous mixtures. The word hetero means different, and so these mixtures look different throughout the mixture. An example of a heterogeneous mixture is that slice of pizza. As you can see the different parts of this pizza.
So what might be another example of a homogeneous mixture? Fruit punch, exactly. With a homogeneous mixture, you have a solution, you dissolve some type of crystal in water, and it looks like one, but it's comprised of more than one. With mixtures, you can undo that mixture, if you will. You can separate the components out. With a heterogeneous mixture, you can see the different components, usually quite clearly, like with a pizza, chocolate chip ice cream, a bowl of cereal, something like that.
See the cheese, the pepperoni, the peppers, and the crust. And so this is a heterogeneous mixture. Let's now take a look at pure substances. A pure substance can also be separated into two categories. To understand these categories, we must think small, much smaller. The first type of pure substance is called an element. And the second type of pure substance is called a compound. Both elements and compounds are considered to be pure substances because we cannot break them down any further into any other types of matter. An element is the simplest form of matter that cannot be broken into any other types of matter with physical or chemical means. You may also know these as atoms, and you may have seen a big list of atoms in your chemistry class on the periodic table of elements. Each square on the periodic table represents a specific element, and that element in the simplest form is a single atom. Each atom, and thus each element on the periodic table, are different from each other. A compound, on the other hand, is actually a combination of elements, and these elements are combined in fixed ratios. You may also know these as molecules. Here's a molecule that represents what scientists believe water looks like. We can see that we have a fixed ratio of elements. These white atoms right here represent hydrogen atoms, and this red atom represents an oxygen atom. You may also know the formula for water to be H2O. Water molecules always have the same formula, 2 hydrogen atoms and 1 oxygen atom. All the stuff in the universe can be grouped into one of two categories.
And so that's just a brief overview in regard to classifying matter, and again, really harping on the difference between mixtures and pure substances. So a lot of what he said we've already got defined here, and we'll just provide you with more examples, so hopefully you'll understand a little bit better. When you have 2 or more different materials mixed together physically the same way you would mix up a batch of cookie dough just by mixing, you've got a mixture. And with heterogeneous materials, focusing at this branch here, or this part of the triangle, the only type you can have are heterogeneous mixtures. These are going to be non-uniform. You can clearly see distinct layers or phases. And let me give you an example of what that might look like. Let's say, for example, that you have a test tube and you have different liquids in the test tube and they have different densities. for example, in one of the labs I worked with, we were able to synthesize long strands of DNA from little chopped up pieces. I don't want to use a big term, where you might have had something simple like a single strand of DNA. You might have had A, C, G, T, C, and from that single little piece you could make a whole long strand of DNA and even double-stranded DNA. And so we had some type of starting material, some basic simple DNA, and when you generate this you have to do it at very high temperatures. So to prevent that DNA from boiling over the tube, we would put a layer of oil here. And what happened here, especially if they were colored differently, you can see distinct phases. So this would be one phase, and this would be another phase. And when you can see these layers or phases, you have a heterogeneous mixture. In the middle here where they met, you would have what's known as the interface. And you actually could generate something like this in a graduated cylinder. Back in elementary school or middle school, you probably did some type of density lab with oils and maybe colored water, and you saw the layering effect. Some of you like salad, and if you have an oil and vinegar type salad dressing, you'll see that one is atop the other. Now in this case, which would be more dense? The DNA. So this substance would be more dense, that's why it's lower in the tube, and this substance would be less dense. So if you were given different substances with their densities, you would be able to figure out where they were in a test tube based on their densities. The more dense substances go to the bottom, the less dense substances to the top. Now if you sprinkled like cork in here and then tried to mix it up, we know for example that cork floats on water. Why does cork float on water?
Because it's less dense than water.
You got it, because it's less dense than water. And we know the density of water in its liquid form is 1 gram per mil. So you would know cork would have a density less than 1 gram per mil. So a mixture composed of more than one phase in which the components are not evenly distributed is known as a heterogeneous mixture. And examples of heterogeneous mixtures we saw in the video, the pizza. Many of you have granite countertops at home. They are comprised of different rock. Whole milk is a heterogeneous mixture. There is 4% fat in whole milk, and if you let it see there, you'll see the layer of fat sitting on top. It's less dense. If maybe you go to grandma's house and she squeezes you fresh orange juice right from the orange, it's not always all liquid. You sometimes have pulp and little strands in there. Chocolate chip cookies, I know they're in my daughter's lunch every single day. Heterogeneous mixture, oil and water, for example, etc. So those are all examples of heterogeneous mixtures. We're not really going to deal with them very much this year aside from in this introductory chapter. And I mentioned that the interface was the boundary. Questions on heterogeneous mixtures? Homogeneous materials consist of one phase. Now be careful, it's comprised of more than one material, but it looks like one. You wouldn't know there's more than one unless, for example, if you had salt water and you tasted it, you would know it wasn't water. And of course you don't taste things you make in the lab because that could be very dangerous. So homogeneous mixtures are made up of more than one material, but they do appear uniform. So you're not going to see these separate phases. You're not going to see the layering. You're not going to have an interface. Homo, we know, means same. And the most common type of homogeneous mixture is a solution. And in a solution, for example, let's say you wanted to make some lemonade. You want to make lemonade or a cup of tea? Lemonade tastes better. We're just going to make a glass of lemonade. So here's your glass. And let's say you start with this much water in it, and you have some type of little lemonade packet, and you pour it in. Well, water is the solvent. It does the dissolving, and the little packet of lemonade crystal would be what? What would that be? Who are you?
Julia,
Okay,
the solute.
you are correct. The solute. Very good. So the solute gets dissolved and the solvent does the dissolving. And so when you have your final product of lemonade, then you have what's known as a solution. And you can't see the crystals anymore. It looks like one. It appears uniform, but it's comprised of more than one. So now you have your solution. You can make solutions from solids and liquids to make a liquid, but solutions can be solids, liquids, or gases. And some examples that are given here: sugar water or something like lemonade, salt water, seawater. Another example of a solution is air. It looks like one, but what is in air? What gases comprise air? What do you breathe in? Oxygen. Air also has nitrogen gas in it. What do you breathe out? Carbon dioxide, and there are other gases in air as well. The gas with the highest concentration, if you will, the highest amount, is nitrogen gas, and so that would be considered the solvent. When you have multiple pieces in there, the one at the highest amount. Similarly, in most of your bathrooms, I'm sure you have rubbing alcohol. Rubbing alcohol is 70% isopropanol. And what that means is that 70% is the alcohol, isopropanol, and 30% is water. And this is a little bit tricky here. Which is in higher percent, the alcohol or the water? The alcohol. So in this case, this is the solvent and this is the solute. If you had 10% isopropanol, then the alcohol would be the solute and 90% would be the water. Another example of a solution is a solid solution, and an example of that would be an alloy. And there are different types of alloys. What's an alloy? So one example of an alloy is brass, and many of you have brass doorknobs or brass faucets in your house. Now, brass is not an element. It's not an element on the periodic table. It's not a compound either. What happens in brass is you have a mixture of copper and zinc. It looks like one, it's a solution, but it's comprised of more than one. So solutions can be liquids, they can be gases, they can be solids, and we'll get more into solutions later in the year. If I asked you whether salt water was a homogeneous or heterogeneous mixture, you would tell me what? Homogeneous. Why?
Because it's composed of salt and water, but you can't see the salt.
Okay, so it's composed of at least two things, but it looks like one. You can't see the other. Also with mixtures, you can undo them, if you will. If you had salt water, you could boil off the water and you would be left with salt. Mixtures are put together by physical means, so you can undo them. And I'll give you an example of that videographically in a little bit. Homogeneous materials that always have the same composition throughout are known as pure substances. And when they're composed of one type of atom, they are known as what? Elements. More than 110 elements have been found or synthesized in the laboratory. We're actually up to 118, although they seem to discover them very regularly now. We can do a check. Maybe we've actually found a few more. And this is a periodic table that shows those elements. Each element has a unique chemical symbol. For example, hydrogen is H, lithium is Li, sodium is Na, potassium K. They don't always start, those chemical symbols don't always start with the name of the element. A lot of them are Latin words, and so they're based off that. Some of them are a little unusual, like tungsten is W, and wherever I point, you'll see the element here. Tungsten is W, gold is Au, silver is Ag, mercury is Hg, carbon, nitrogen, oxygen, which you would be familiar with from biology, sulfur and phosphorus as well. Each chemical symbol is either one capital letter or a capital letter followed by a lowercase letter. And you can see we're up to element 118. And now you can also see that some of them are named for where they are discovered. So clearly in Moscow. So as I said, each one is unique. It has a unique set of physical and chemical properties. We'll talk about that in the secondary lesson. And it involves a 1, 2, or 3 letter chemical symbol. Now here's where I think some of the molecule confusion came in earlier. They can exist as single atoms, like, for example, lithium, Li, or they can be molecules. For example, if you have hydrogen gas, it's always H2. If you have oxygen gas, it's always O2. A molecule consists of 2 or more atoms combined in a definitive ratio. We're going to get to that in the Pogel packet. They can be the same or different elements. It can be a little bit tricky there, but the Pogel packet's really going to go into that, so I'm going to hold that concept for a little bit. When you have substances made up of 2 or more types of elements that combine chemically, so not physically, you're not just mixing them together, they're bonded to one another. They're not elements, but rather compounds. Oops, I lost the L. How better. These atoms are in definite ratios. So for example, H2O, 2 H's, 1 O. And we'll talk about counting atoms in the next chapter. And they are represented not by a chemical symbol, but rather by a chemical what? Starts with an F. formula. In that chemical formula, you have to have at least 2 capital letters. Let's try and determine if these pure substances are elements or compounds. So carbon is an element, and carbon monoxide is and cobalt, which looks almost like carbon monoxide with one key difference in terms of their chemical formula versus chemical symbol, is an element. Potassium is an element. Potassium chloride is and glucose is a compound. And let's just make note of carbon monoxide versus cobalt. So they're both CO, but carbon monoxide is big C, big O, and cobalt is big C, little o. Cobalt is a metal. Carbon monoxide is a colorless, odorless gas that can kill you. In Florida, we have a lot of hurricanes. We do not start generators in the house. We do not keep generators in the garage. We do not start our car in the garage with the garage door down. And we do not pull into the garage, close the garage, and then turn the car off. Many of you are starting to drive your new drivers, and in today's world with so many quality technological distractions, you're not always paying attention. Be careful. In Boca, several years ago, probably 10 actually, many years ago now, a mother came home with her daughter and her best friend, pulled into the garage. The kids went in the house, so did she, closed the garage. And the next morning, only one person was still alive. You do not leave the car running with the garage door down. The carbon monoxide will build up. It will enter the house. Carbon monoxide. Carbon monoxide is a deadly, odorless, colorless gas. You can't see it. And by the time you realize it, it's too late. Be very careful. If you don't have carbon monoxide detectors in your house, you should. Before I bought my second to last car that has that push button start, my mom pitched a fit. So my dad, even though I'm a grown-up, my dad ran out and bought a little carbon monoxide detector, and he let himself in my house and installed it. And it's not really a big installation. You plug it into an outlet. But she wouldn't let me have that car till that thing was in the house. And it doesn't matter how old you are. You listen to your mommy, because she's always right. All right. Be careful there, though. You're driving. Be careful. Life lessons. Okay. There are some key differences between mixtures and compounds. This is a short little video that will clearly illustrate what's written here, and I'll point it out as we go. But this is really very cool.
In this experiment, we will first make a mixture of black iron filings and yellow sulfur powder.
So you have 2 elements.
Black iron filings and yellow sulfur
That's
powder
iron and sulfur.
are thoroughly mixed.
Couple things to point out here. You have 2 solids, you mix them together, you still have a solid. Mixtures have properties of those components that went into them.
They form a gray mixture of the 2 elements. This mixture can be separated by physical methods. For example, when a magnet is brought to the mixture, it removes essentially all the iron filings, leaving the sulfur behind, which here looks gray because of the impurities from the iron. The iron has been separated from the sulfur by means of a magnet. When the same mixture is heated in a test tube, the 2 elements iron and sulfur react together to form a new compound, iron sulfide. At first, when the mixture is heated, the sulfur melts. Eventually, as the heating continues, the iron and sulfur begin to react together. When the Bunsen is removed, the tube continues to glow as the reaction proceeds. The gray-black brittle solid formed is a new compound, iron sulfide. It is unlike either sulfur or iron and cannot be separated by a magnet.
So the compound has properties different from the elements that comprise them. And that is a key difference between mixtures and compounds. And that's what's indicated here. So hopefully you understand the difference between a pure substance and a mixture. Pure substances come in two types. What are those two types? Endora.
Elements and compounds.
You got it. Elements and compounds. If you have a single type of atom, you have an element. If you have more than one atom, and you've got two different types of atoms, I should say, that combine chemically, you have a compound. When things combine physically, you have a mixture. You've just mixed them together the way you saw it in the videotape. So at this point, you want to have some understanding of classification and be able to identify some examples of each. Okay? The lab you're going to do on Friday goes into pure substances versus mixtures. So that will be made further, hopefully further clarified there. And I've got a POGL packet for you to work on. So we're going to end this lesson here. Hopefully in regard to the classification, you have a better understanding. And what we'll do in the next part of the lesson are properties and changes of matter. Questions?